All right, for people joining this live stream, this is a design review of new functionality in, we seem to have somebody who needs to be muted, by the way, functionality in geometric computing. And this looks like a mega design review, which I can't imagine we're going to get done in the next hour, but let's at least start. Wow, okay. All right, so should I be running this in the prototype build? Or is it not worthwhile? Is there no point in this particular file being run?
Should be fine, the prototype build.
Okay, but I don't know whether I can run DocuTools in the prototype builds. But what should I do here? Should I look at? Okay, where should I look here? Should I look in Polygon guide / polygons new or what?
Sorry, okay. Can I just talk you through it a little bit first, and then we start looking?
Okay.
Okay. So By
the way, I'm sorry. Who is project managing here? Is it Manu?
Yeah, Stephen.
Okay, so you should report that in the prototype build here. I think this is a prototype build. It is unbelievably slow to type in the search field here, and now it says it can't find it.
No, because it's only in source.
Okay.
They're not built. You know, that's what we call them before we transact.
Okay, that's fine. Okay.
Now, so first of all, this first section here, and you might want to browse through it. If you close that polygon before opening, just close the polygon cell so you can see bigger structure. The big polygon, that one. Okay, that's Polyhedron. Close that.
Yeah, I already looked through this.
Oh, you did. Okay, so you have a sense.
I have a sense. There's a lot of stuff here. Looks wonderful, but there's a lot of stuff.
Okay.
Okay, so let's. Okay, so first point is polygons with holes and other such things.
That's correct.
Wow, a lot of interesting stuff here. Really interesting stuff. Okay.
Okay.
Cool. Polyhedra.
Same story there. The polyhedra with voids.
As well as named polyhedra, which we've already got. Polyhedron data. But that's presumably now feeding into these polyhedra, right?
Yes, so they will be able to return those, and we have a new thing called uniform polyhedron, which is one of those easy constructors.
Okay.
As well as, and I realized that it's not added here, Charles, we forgot the platonic solids.
Oh, right.
We've introduced those as just standard names. So icosahedra is a...
Icosahedron is just a thing now.
It's just a thing now. But there's just 5 of them, you know? So,
yeah, I understand.
Now,
I wonder if there'll always just be 5 of them, he says. No, I'm just joking. Okay.
There definitely will.
Okay, so then if I say graphics 3D of that. Okay, and that presumably has, like a sphere, it presumably has something where I can say 0007 or something.
What would 7 do?
Does a radius?
So it's the other way around. You should probably open the, reference page. Let's describe.
And that would be the consistent thing to do, wouldn't it? That's what we've done for many other kinds of things. And that says icosahedra. Shall I fix that? Or you can fix that. It's futurized anyway.
It's correct. Even
it says represents a collection of icosahedra.
Oh yeah, right. Dodecahedra. Yes.
And those P20s are wrong. Oh no, they're not. Sorry, P20 is correct. It's the dual. I don't quite understand this. What I don't understand how this aggregates here. But we got a bunch of background noise. I don't really understand how that's aggregated there.
So first, in terms of modeling, the parameterization is in terms of the length of the edge, center at 0, 0. And the third usage gives you the rotation, theta phi.
Yeah.
And the last point, like you guess the 0, 0, the first argument allow you to do a translation.
Okay, all right, we'll come to this. Okay, this is ridiculous for me to dive into this particular thing. By the way, somebody on our live stream is asking if Voronoi mesh for 3D is being worked on.
It is, but it's not coming now. Part of what we're doing by having Polyhedra is needed as an actual cell for mesh regions, and the cells that's produced by Voronoi mesh in 3D are general Polyhedra, and so that's needed there.
Okay.
So it's coming, but not 12.1 probably.
Oh boy, there's a lot of stuff here. So planar angle is what's going to just do 3 points, right? That's the planar angle between 3 points.
Yes.
Aha. So if I say, for example, here, if I fix my polyhedron, my dodecahedron thing there, if I say, for example, surface area, cool.
And now if you have an L, you'll probably get a parameterized form. Or A, or whatever side length, edge length.
Well, good. That
was not the most complicated.
Wait. How can it be linear in the edge length? Why isn't it quadratic in the edge length?
That's a good question.
Something weird. I would suspect a bug there. And also, why is it different? Why is it a different functional form when it's got an E there? Well, that could happen, I suppose. Well, anyway, never mind. That's, I mean, obviously to look at. And the volume of this creature is this is a filled dodecahedron, yes?
Yes. They're all solid.
Okay. Okay. Wow. Okay, a lot of stuff here. All right, let's dig in here. So let me get some sense here of the polygons with holes business. That seems scary to me.
Mm-hmm.
That's polygon, but I want to say polygon new, don't I?
Yes.
Okay. Represents polygons with holes.
So what we've done before, we have a multi-polygon since before.
Mm-hmm.
Okay, but that is effectively a union of polygons.
Indeed.
Okay, so we can't just use lists. So we use a rule. So the outer left and then the inner.
So is the inner a complement type operation? Is this thing a complement?
Yes. That's what it means.
So let me understand this. Okay, so there's a list of things, and then there are complementary holes that are popped out.
Mm-hmm.
So if there's a lake on an island on a lake, do we get to say that, or does that not make any sense?
So you iterate, you mean?
Yeah, I mean, in other words, if I were to have, in this case, I have a polygon and I punch a hole out of the polygon, right?
I mean, it's still, I don't know if there is an immediate direct way to do that. Of course, it can be represented. It's not a problem. It's still a polygon. In our
yes, I understand. So, okay, so what is the thing that punches a hole out of a polygon? There must be an operation that does that, like polygon complement or something. That given one polygon
region difference.
Okay, so in other words, if I say, so if you're telling me, if I say triangle, how do we have this? If we say SSS triangle, why doesn't that make well, it should make an equilateral triangle. What the hell is it doing? Why isn't that making?
I think that they're individual. I don't think that's a list.
Okay. Okay, fine. So there's a triangle. So now if I say I want to punch that triangle, so I say region difference of rectangle, and then %50. Well, actually, what I really want, let me make those much smaller, okay? I don't really know what I'm doing here because I don't know exactly where it's going to land up, but okay. And now that's going to be a little bit on the corner, unfortunately. Okay, so now if I say graphics of that, oh, whoops, what did that do?
So first, we are still working on that. We haven't yet, here it's still generating a Boolean region. So you have to do a region, actually a region or region plotting.
Okay, that's a bug.
Just do a region of 55.
Okay, but that's a bug, right? We agree?
Yes.
Well, whatever. I don't know what I did here. I don't understand why that wouldn't have punched it out. Whatever. I don't know. I don't exactly understand that. But should that have given a polygon with a hole as the canonical form, or is that part of canonicalized polygon?
That's part of canonicalized polygon.
Which probably should be called canonicalized polygon, not canonical polygon, I think. But I may be wrong. Okay. So I understand what's going on here, I think. So you're saying this polygon. Now what happens if the Q sub I are not planar with the P sub I? Well, what happens if the P sub I are not planar in 3D? What happens in general?
So in 3D, in graphics, it's sort of undetermined what's happening. It's running a triangulation library, and it does something, but you cannot predict what it will do.
Okay.
Okay. So a non-planar polygon is largely, it's an undefined, sort of algorithmically defined. It depends on who implemented it. If Joe Bob has a good mood that day, or.
Yeah. Okay. By the way, this is not tagging what's new in 12. Just a comment.
Right.
Is this new? This thing at the end?
Yes. So the idea is that that case there is basically like a complex, like a graphics complex.
Right.
Okay. Which is it's part of what the canonical thing will do. The other thing you have to remember, we can't prevent you or users from giving loops that cross themselves.
Sure.
Okay. And we can't also prevent you from giving these inner loops that either cross themselves or cross the outer loop. So there's a lot of things that can go wrong with polygons, and Polyhedra even more.
Okay, but so this case is like a graphics complex. So you're saying...
Yes.
But so what is the form of data typically?
Okay, should be down there. And those are just indices now.
Yeah, I understand. Okay. So what is this now? Outer polygon points and inner polygon boundary. What the heck is this? Oh, I see. So this is an inventory. This is a library of points to use, and this is now specifying the actual structure of the polygon.
Correct.
Okay, it's reasonable enough.
And this works exactly the same way for Polyhedra, you see.
Yeah, I understand, which is nice. Okay, let me look at the Polyhedron page. We've never had a Polyhedron page before.
That's right.
But it's still called Polyhedron New or not?
It is.
No, it's just Polyhedron. It's the guide page, which is Polyhedron New.
Oh, sorry. Yes.
Do you realize that we're not beeping in real time anymore?
Yes.
That needs to be
some
fixed.
other Mac user told me that.
Okay, Polyhedron. Inside the closed surfaces with polygon faces. represents a polyhedron in the voids. Okay, so in other words, if I give you, so fundamentally what you're telling me is if I say, boy, that's a big mess. If I say polyhedron data of rhombic, whatever it is, rhombic hexaconahedron, comma, faces, that's a bit funky. What do I want to call it? Face coordinates or something?
I don't know.
What is it called? Well, what I was going to do is feed that into the polyhedron function.
Well, you can, okay? You can get the coordinates and the faces, and it will fit right in.
How do I get the coordinates of the faces then?
Just ask for the coordinates in polyhedron data.
Vertices.
Vertices.
Oh, look at those. Those are very swank. It's the first time I've seen those in the wild.
Well,
those are nice.
Yeah.
Do you like those, Roger?
I do. And we have something even cooler for Club 1.
For what?
I'll talk about it later.
No hint?
No.
Okay, fine. Okay, that didn't work.
Right, because now you need also the faces.
I know, that's what I thought I was going to generate from this. That's why I was trying to do faces.
But polyhedron need both coordinates and faces.
No, I understand that. I understand that. So I'm saying that this, and presumably that, if I say this, but this is very weird that I have to do it this way, right?
No, I don't know why. Why don't you read the documentation, follow it? So the first position is points, right? The vertices. Second position are the faces.
But this says faces, F sub I.
In polyhedron, coordinates, comma, faces.
No, it doesn't. That's what it just says.
Right, but you couldn't get that data directly out of polyhedron data. I said, it's okay. You don't need that in that form.
Okay.
Okay. I mean, you probably can get it out. I just don't know what it is.
No, I understand. But how are the faces specified here?
The faces are just a list of points. Okay. So each one is a face is a polygon. Okay.
It's actually a polygon, or it's a list of points. That would be
list of points.
Could it also be polygon of list of points? Should be.
I assume so.
Charles,
is that supported now, or we should?
No, we should probably go there. I mean, there is that whole thing that we have to propagate it all over the system for polygon, line, point, and such.
Oh yeah.
So that's for later on.
I'm sorry, no. If you say it's got faces, we should be able to, polyhedron should be able to take symbolic polygons as faces.
I agree, but we have to do that through the whole system uniformly. You remember midpoint need to take that. Everything need to take point or line. The same for line, right? Line need to take also point. So we have that the whole system. So we are thinking at some point.
But I would do it for polyhedron because it's going to be super confusing to people immediately for polyhedron. I mean, I agree, you need to propagate it through the whole system, but I would make sure it works with polyhedron.
Okay.
But Stephen, if you just want to make your example work, the one you started, then
yeah.
Okay, can we just make that work?
Yes, I mean, I thought I was going to make it work this way because I was going to make it work. I'm just surprised. Okay, who is Aaron Weinstein is the person dealing with polyhedron data, right?
Yeah.
We in contact with him.
Yes, of course.
Okay, all right. So then, how do I get?
Can we?
Well, if you just two polygon faces, comma polygons, it will give you that.
No, where's polygons here?
So polyhedron data take a third argument. So you can say like you did faces, and if you put comma polygon, then it will give you actual polygon object.
Okay, this has to be better documented. Well, it doesn't even say other output types related to this. It doesn't even list. It doesn't list polygons here. Right?
Yes.
Okay, so there's some cleanup needed. So this is now
No. So the first one should be vertices.
I thought it should be faces. And then you say polygons there.
But
Right.
will that work? Because then it probably comes out the polygon and it still don't work.
So then you have to drop that, right? Drop the head, then you get your polygon.
So what do? I say polygon goes to identity?
I think so.
Okay. And now finally polyhedron, right?
I'm not sure if the levels are correct here. I don't know.
I think they are. So now I say graphics 3D of this. Sploff.
No, it.
So this should be a.
There will be an easy
point.
out. It will get you a polyhedron out directly. Okay, it doesn't right now, but it will.
I think there's one extra level of list here. Ta-da! Okay, so listen, there's some cleaning up to be done, Charles, with what polyhedron data generates, and maybe some other properties for polyhedron data. That makes sense.
Yes, we have been discussing that with Eric, so it's in the plan.
Okay. So are you telling me that if I now do this, and I do, for example, like a sphere or something, I can do the Boolean whatever it is of this with a. How do I get the size of the circumsphere around this? Circumradius of this.
Bounding region of the points. But I don't know if that's
probably won't work.
Probably won't work. It's not installed. But if you have the points, just do bounding region of the points and you'll get it.
Well, actually, I don't have the points here because I'd have to get the vertices. So this is a bit of a mess. Okay, so if I say bounding region.
So that will give you a cuboid, but then you want a min ball.
Yeah, how do I get that?
The second argument is min ball.
Of which?
For bounding region. Bounding region can produce many different kinds of bounding regions, and you want the ball. There it is.
That's super cool. Okay. So if I say, okay, so here's what I want to do. I want to take this and I want to do a Boolean. How do I chop? I want to complement with that ball. So I want this thing with its points chopped off. See what I'm saying?
Yes. Will that work now, Charles? Is that all installed?
No.
Okay, then
it won't work. Okay. But that stuff is coming, yes?
Yes.
Yes.
Okay. All right, so the fundamental point here, by the way, I assume that the last level of lists, if I have only one hole, is it the case that I can drop the second layer of lists on the complement side of polygons?
Yes.
Okay. It's very interesting. This polygon hole thing is very interesting. I don't think okay. Okay. Canonical polygon.
That will produce whatever input you use to insert, so the input to polygon is rich. But if you're going to compute with it, you want it in a form that's useful for computation. And that's what canonical polygon.
By the way, I assume that the famous examples of South Africa with Lesotho and things like that, that we're going to return these richer polygons in the future from our. Have you talked to the geo people about that?
Yeah, Jose is ready to go. When this is live, that's what he's going to leverage to build that layer for geography.
Wonderful. Wonderful.
Yes, yeah, we've been since the inception and before.
Okay. All right, canonical polygon. Do you really think that's the right name as opposed to canonicalize polygon or It's a little weird. It suggests it's a special polygon, so to speak, as opposed to something that takes a polygon.
I don't really have a super strong opinion. I think canonicalize as in verb is not bad.
Well, for precedence, you have canonical graph who does something similar.
What does canonical graph do?
Give a canonical form of the graph isomorphic.
That is a very crazy message there. Gives a canonical graph of the graph. Can I change that? Gives a canonical form of the graph?
Yes.
Okay. Well, what do you think? I must say I'm a little bit weirded out by canonical polygon, but let's understand what it does at least. So what are the different filters that you can use here?
So one thing that can happen, and that frequently happens, is you get...
By the way, I'm sorry, the filter specifications that you've given here are not strings. So the quotes filter is the wrong specification there.
True. That's true.
Minor point.
Right. You're right. You know, so the main thing that's important there with filter, so when you do Boolean operations, it's not like if you do Boolean operations of 2D solids, you know, so areas.
Mm-hmm.
What can happen is that you get lower dimensional components come out. That can be line segments, that can be points, for instance. Also, in our specification, allows you to specify these, quote, singular, if you like, polygons that are just lines or just points. Now, a lot of operations, you don't want to deal with that, and you want to work with what's called a regular closure, which is the interior. You compute the interior.
Oh, I'm just going to put that up there because I'm sure it's a keyword for this.
It is, yes.
Okay.
Which you compute the interior that blows away all the lower dimensional stuff, and then you compute the closure, and then you get the boundary points to be included. Okay, so that's a regular closure.
Okay, but the picture you've shown here, I would have expected that from canonical polygon.
No, I'm just saying you asked about filters. Okay, the picture has nothing to do with the filters.
Okay.
The picture has to do with the base case that everybody thinks about. You can think of it as actual outer and actual inner. Okay, even if you don't specify it like that up front. Okay, like that star was generated as one self-crossing line.
Yeah, I mean, surely. Yeah, these examples are hardly stellar without any pictures.
Agreed.
And also these examples where they just give the same result back again are kind of silly.
No, definitely we are working on the example. If you want example of canonical polygon on the review notebook, there are examples there.
Oh, okay. That's a new function, polygon coordinates.
Yes.
Why are we doing it that way rather than having a coordinate sub thing from a polygon?
Because you will be using it if you actually directly compute, and a lot of people might want to do that, then you will be using it a lot.
So question, my gosh, that's new, that's exciting. Yes. That's interesting, it's a good idea. Now, why didn't this come back as one of those?
Because it doesn't auto-canonicalize.
Well, and also, you know, to avoid noise during the development process, we just did that for the canonical version. So if this is approved, we probably will propagate it everywhere if needed.
Do we want to call it polygon coordinates or polygon points? Polygon vertices, polygon, isn't it polygon vertices?
But I mean, the actual output are coordinate, right? If we say point, you should return point. Vertices.
Well, vertices would be either, but I mean, that's if. Okay, question. I mean, we do not have right now subvalues for the. Do we have subvalues for any of these geometric things, or regions, for example?
We have some, but not really documented or usable. There are some in region.
Some what?
There are some subvalue in region.
Okay. Would you consider having subvalues for Polygon?
No, not really. From the experience from region, it didn't work that nicely. So, but it's possible. I mean,
Okay, so a second. So am I to understand that we have both polygon coordinates and polyhedron coordinates as two separate functions?
Yes.
Is that a good idea?
Well, so really, they're really, kind of simpler forms of boundary meshes, boundary mesh regions. I think that it is just this triple of functions: polygon coordinates, inner polygon, outer polygon, and the same thing for polyhedra. Same triple, or in the canonical 4, I guess.
Yeah.
I think that
you're not concerned about the fact that we're going to have something which is, I mean, okay, naive question. I mean, if we started to have like CAD-like things where there's instead of a polyhedron, it's something defined by, NURBS or something like that, some creature defined by NURBS.
Mm-hmm. Well, so here's a concern, okay? I think that where we build up, part of what we have rich is mesh region, boundary mesh region, and those are going to get richer still.
Okay.
But I still think from people's mind, there's a whole group of people that think polygon is the whole world.
Mm-hmm.
Okay, and I think this appeals to them. You can do a lot of computations directly on there.
But you're proposing then that the fancier stuff like random NURB created things are boundary mesh regions.
Right. Okay. There will be probably a new object because mesh will probably stay linear, and once you go non-linear, it's a new object again.
Okay.
Because they're going to have other issues.
Yeah. Okay. All right, but you're proposing. Okay. I get it, at least. Okay, can I try this with that, just for the hell of it? No, didn't work. Oops.
Well,
did I get rid of? Oh, I got rid of it. Too many layers.
Right.
Oh, you had it correct. Sorry. Okay. Okay.
So the polygons that you get back from these are simple polygons. They're homeomorphic to a disk.
Yeah.
Oh, well, not always, right?
How do I get the holiness of this Euler characteristic, whatever you call it, of this thing?
Do you mean for polyhedron Euler characteristic?
Yeah, I mean, it's the same thing, Euler characteristic for a polygon, isn't it?
Yes.
Yeah. Well, we just have for polyhedron so far.
Why don't we have Euler characteristics for polygons? It's perfectly happy. There's a holiness count for those too.
Right.
But so there's a function Euler characteristic that just gives this. Is that right?
Yes.
But it doesn't give the holes. It gives the Euler characteristic.
No, I understand, which in this case would be, 2 or something? I don't know how they count. What about genus? I mean, isn't that?
We also have a genus, but for polyhedron so far, so we can extend it.
Okay, make it work for polygons. It'll be easier to document. We don't have a thing called genus. What is it? What is it? What is it called?
Polyhedron genus, I think.
I think we should just have a thing called genus. Is there any reason not to do that?
Well,
or region genus?
Okay, but I don't know if we can compute it for regions in general.
I see.
I mean, we will eventually, but
well, okay. So initially, you want to have polygon genus, polyhedron genus separately. Is that the idea?
Yeah,
I think it's fine. I mean, eventually, we may be able to have a more general genus thing.
Yes.
Okay. By the way, somebody on our live stream asked kind of a separate question a while ago. Come on, finally import-export polygons and regions to STL files with textures.
No, not currently.
STL doesn't support texture.
Oh.
OBJ, yes.
OBJ, yes, but
we support it when possible so far. So it's
okay.
But I think there was one thing we needed to update, wasn't there? It was the texture support for meshes.
Yes.
Okay.
If you carry it in a normal graphic, we kind of do that, right? So.
Right. Okay.
So
it is supported where it's supported in the objects.
In the external objects.
Also internally. So you can import it and get a graphics complex, and you get the texture.
Mm-hmm. But you're saying for the mesh for regions, we don't yet have textures.
Right. We don't meshes, which is the one that would be relevant, don't support texture coordinates right now.
But can one convert from a mesh to a graphics complex?
Yes. Using
what?
Show.
Okay. And then you can have textures.
Yes.
Okay. This is another complaint that this doesn't work.
Yes, we'll get there. It's a union, so we are working on that. As soon as we have everything working, it should work. It will work.
Okay. Wait a minute. So this is something that's coming in this version or not?
Well, this version or the next.
Okay. There's a question about high performance 3D graphics. Yes, that's coming, but not for this. Not this discussion. Okay, somebody is commenting that biological genus is better known, and we shouldn't probably use the word genus to represent. Good point.
Yeah, that's a good point.
I mean, ultimately, it should be region genus probably, or geometric or topological genus. Maybe the correct term is topological genus.
Yeah, we'll come to it.
Okay. I think it'd be nice to start having some functions that have topology in their name.
Yes, there's a whole slew of things for topology coming.
Like what?
A lot of things related to algebraic topology and combinatorial topology.
Okay. All right. So. Okay.
And we have a bunch of other things already in Pointset topology.
Like?
If you go to semi-cylindrical decomposition, it's actually, we support Pointset topology operations for semi-algebraic sets.
Cylindrical decomposition?
Yeah. Now, if you scroll down there, okay, these go up. One more, up there, okay? Topological operations. Boundary, closure, interior, exterior, closure.
I have no idea we added these. Wow. I mean, wait a second. So that means, I mean, those are pretty non-trivial things. I'm surprised that those are hidden down in the properties here.
Because we're going to bring it out in a more broad sense. This is one corner of it that needs to be a lot more support.
Okay. But this is basically taking...
Yes, they're non-trivial.
Right. But I mean, so what this allows one to do, I mean, in your polyhedron thing, you would be able to take cylindrical decomposition.
But you don't want to do that, okay? You don't want to do that.
Do what?
You don't want to use cylindrical decomposition for polyhedra.
No, I understand. But given that you've got a solution set from cylindrical decomposition, you could turn that into a polyhedron that you can then compute with.
Right. In principle, if you wrap it in implicit region and you call canonicalize, yes. I mean, that's
Why
the
does it have to be an implicit? Well, anyway, but let's not go there right now.
Right.
Okay.
We can have a long discussion about that.
Okay.
You don't want to.
Fine. Let's not derail this. Okay, winding numbers and things. Is there some? Okay, so let's look at outer polygon. Does outer polygon have some kind of way of deciding?
These are utilities. No. These are very utility things. Okay. So outer polygon, if it isn't already canonicalized, it will canonicalize first. Okay, and then that defines what the outer polygon is.
What does the canonicalization operation do again?
It does a number of things, but you see the example given there with the star.
Mm-hmm.
Those points where it crosses, those have to be computed.
Oh, I see. So it starts as a polygon with a winding with just a bow tie-ish polygon.
Right.
And then
there can be other definitions of polygon, which you'll see that we also support. Okay. There are different ways to give meaning to polygons, particularly when they are non-simple, when they cross themselves.
Yes.
And they define different regions. Okay. So there are constructors down there, a crossing polygon and a winding polygon and a random polygon.
I'm still not, by the way, completely sold on this name, Canonical Polygon. Can you explain more what Canonical Polygon really is? I mean, it's a polygon. I understand it's been canonicalized in some way, where it's been explicitly written as a polygon complement type thing.
Yes.
So there's one key thing is that you can have several ways to, one polygon geometric region in R2, for example. You can describe it in several forms, just using our expression polygon. So canonical polygon first allow you to have a standard representation, one unique expression.
Yes.
And what we do is that we canonicalize, for example, the coordinates, which are sorted. And then you have the indices. And from that, you can actually deduce a lot of operation or resolve for operation from sample to duplicate coordinate and such.
Okay.
So it kind of does the cleanup for you before you actually start to manipulate the object.
Reasonable enough. All right, let's take a look at some of these other ones.
So the definition of crossing polygon is if you pick a point. Now that point is in the polygon if you draw a ray to infinity, any direction. And the number of times you cross the boundary curve
is odd.
Okay.
Yeah. Okay. So it has a point for away from the point, representing all points for which a ray from the point in any direction of the plane crosses the segments. So that means any of these corner points.
Right. But now to get it to totally unambiguous, you should not pick a corner point. You should, you'll cross a corner point with probability 0. It has measure 0 if you pick one array at random, okay? And you can surely pick one that doesn't cross them. If you cross them, you need to compensate correctly. So don't do it. It's that simple.
Yeah, okay.
Okay. So now the definition is unambiguous, and that works exactly the same way for a polyhedron, for a crossing polyhedron. It works in higher dimensions than that. In any dimension, actually.
By the way, what are we doing for higher dimensions beyond 3? Are we going to have polytope eventually?
Eventually, yes.
Okay.
But clearly, it's more important to get really good coverage in 2D and 3D.
Sure.
Okay. Now, the other new thing here for this one, if you look at the two triangles down there.
Yeah.
Our definition of polygon that we instituted and canonicalized on in version 6. So you had the same definition everywhere in printout and screen and different platforms, is the one that's called polygon. It treats multiple loops as a union. However, you can very well treat them as just loops in this condition where you put array to infinity. And that's what crossing polygon does. So it does a less naive and richer construction. And it would produce a polygon out that is like any other polygon. So it's a constructor.
Okay, here's the thing I'm missing. So I understand. Let's see. Okay, so these curves, so this is just P1. This is the line segment, but these are P12, P21. I think this is a oh, I see. This is a higher dimension. No, I'm totally confused here. A line segment just is defined by 2 points. Why is this saying P11, P12, dot, dot, dot? I think that's wrong. I think you want to say crossing polygon of P11, P12, then P21, P22. Isn't that right? Do you get what I'm saying?
Not sure.
No, look. These the line segments, what this is doing, right, is just breaking this as partition 2, 1, right?
Yeah, so those are the faces of the polygon, if you like, the edges.
Yes, right. But what this is saying is these line segments, if you had more than 2 points in this line in this thing, it isn't a straight line. Right?
No,
so
it's made up of edges, the segments.
This is the full closed contour we want to specify. It's kind of the multiform like you have in Polygon, right? You have a list of.
Oh, I see. It's
the multiform, but it's interpreted differently. That's what I was trying to tell you.
Okay, so this is very confusing. So what you want to say here, this is confusing. Let me understand some of these other ones first, okay? Mm-hmm. You're not trying to get too, I'm sorry, I'm just going to ask a meta question because I didn't fully understand what you were talking about there. You're not trying to stuff 2 different definitions into one crossing polygon thing, are you?
No, it's the same condition that I said with array. Exactly the same condition. But even that first line of illustrations there, look at that last example.
Yes.
It has 3 closed contours.
Mm-hmm.
Okay? And they're all viewed, when you decide what points are in it, that ray condition is still applied to all of those contours.
Mm-hmm.
Okay? Whereas in Polygon, that would just be a solid rectangle because they're viewed as a union.
Yeah, I understand.
Okay? It's different.
Okay, so I don't completely understand the word crossing polygon.
It's ray crossing.
Is it a standard name?
It's
ray crossing, right?
Yeah, it's
all right, okay, let's keep going. We have some questions on our live stream about will this be useful for
so there you have your lakes example, by the way.
I understand, right. It's
okay. This allows you to do that very easily.
Okay.
The lake on an island.
Let's see. This is now comments on our live stream about defining a polygon by having the polygon vertices in counterclockwise order. Is that what winding polygon is going to do?
Right. So winding polygon, depending on the orientation there, right? Yeah. So you can specify that using winding polygon. It doesn't matter for crossing polygon the odd way per se.
No, I understand. Represent a polygon for which the closed contour winds around at least one. You mean once here, not one, right? Once.
Once.
The closed contour winds around at least once. Boy, it's hard for me to understand this stuff.
Can we change over to my screen for just a bit, Stephen? And I think it will be useful for you and for the audience, everybody.
Okay. All right. Hold on 1 second here. I just want to see. I'm just excited by random polygon. I just want to see what that is. And then we can look at your screen, Roger.
Okay.
Oh, wow. That's a cool idea. That's a really cool idea. So So if I say graphics 3D of that, I actually will get all of those 3 polygons in the same,
graphics.
Graphics. Now, what if I wanted 3D polygons?
We have a second argument, or third argument, I believe, which gives the dimension.
You can actually get them in 4D too if you feel like it.
So that just gives the number of polygons, but how many sides do the polygons have here?
The second argument is the number of sides.
So you can do convex comma 3, 5. We give the number of points.
Wait. 3. I thought that was the number of polygons. The second argument.
Yes. But you can put convex. You can put it in a list. Ellipse convex comma 5.
Okay, so there are random hexagons. Planar, yes, because all polygons are. Okay.
Yes.
Wow, we've never been able to do this, have we? Getting random polygons in 3D that are guaranteed planar.
Right. Actually, much more interesting is if you do simple.
Okay, what's the point of that now?
So they're still simple, but they're not convex, right?
Oh, I see.
What's that?
Yeah, what the heck is that?
Oh, I think it's the rendering, the buff filling. The rendering method, they are too close together, right? The polygon. So you have that buffer filling. It's depth filling, right, Roger? What do you call it again?
That only comes in when you do opacity, so I don't think so.
I think it's a bug. Shall I send you this collection of polygons?
Yes, I'll talk to you.
Okay. I'll just send you that cell. Okay, hold on. Oops, this is not so easy. Why is this taking so long? Oh, that's really weird. Did it just render this? That's crazy. It just rendered this as a graphic. Oh, you know what I should do? Why doesn't that offer to, at the cell level, it should offer to copy as input text, right? But why didn't it do that when I selected the graphic? That would seem to me to be a minor bug. Okay, let's watch Roger's screen then. I'm not completely convinced, by the way. In terms of this documentation, you really should put something which indicates that there's this list n thing at the top here. I'm also not at all convinced that the dimension d should be a third argument like that. I think the dimension d should be something that is somehow part of, more like d arrow, whatever it is here, for instance. Making sense? Because I think the d is like a critical piece of the random polygon. What I would suggest is something more like this. Random polygon, 3 arrow 10 for 3-dimensional 10-sided polygons, which means that you'd end up with things like 3 arrow convex 10 and things, which seems to me much. Does that make sense to you guys? I think that's better.
I think so. Because you're rarely going to specify it.
Specify what?
I mean, I guess 3D is very mainstream. Higher D is not so mainstream.
Sure. It's going to end up being, 3 arrow 10 means in 3D make me 10 things, right? But 3D is very mainstream, so you don't want it as a third argument after having a 1 there.
Mm-hmm.
Okay, make sense?
Pretty good point. Yeah.
Okay. Okay, let's watch your screen.
Okay. So here, can you guys see?
Yep.
Okay. So I'm just going to spend a little bit of time, but then we'll understand all of these definitions much better,
Okay.
I think. Okay. And so, so here's the ray that we know called crossing polygon.
By the way, Roger,
Yeah.
what are you doing with these documents? Are these going to find their way into the notebook archive at some point? Because there's really a lot of great material here.
They drive a lot of our development.
Yeah. Anyway. Okay. All right.
Okay.
Encyclopedia. The Roger Encyclopedia.
Sure. Okay. So. Okay. So. So first of all, we need to sort of. I'm going to define the ray crossing, which we talked about. So we have a piece for polygon. We have a piecewise linear curve, right, in R2. And the ray crossing counted the number of times a ray from P to infinity, any type infinity crosses C.
Okay.
That contour. So now we can define, for instance, a polygon, a ray crossing polygon, is the points for which that ray count is odd.
Are we going to have this function, ray crossing count?
We do, actually. Okay. So if you scroll in that design notebook that I sent, it's just a few lines below. Okay. Now, if I have multiple contours, so I have multiple of these closed contours, then, the ray crossing count is the total number of times the ray crosses any of these contours. And now I define that polygon very much the same way. Do you see what I'm saying? I'm just saying that the count is going to be odd. Okay?
Okay.
So that gives you an algorithm, and let's skip that for now. But now we can do, so here's so the question is when they are similar. So this is a simple polygon, and it behaves like you think, So these guys have a crossing count of 1, crossing only 1, so it's in. Here's a simple. Sorry, that was a convex polygon. That's a simple polygon, and here is a non-simple polygon. Okay, so in here I'm crossing. Here I'm crossing 2 times, right? So those points in there are out.
Yeah, I get it. That was nice.
Those are in.
This function random membership plot should make it to the function repository.
Right. Okay. Now here's the case with that multiple contours. See, again, the rule works, right? You pick a point here, I'm crossing twice, it's going to be out. I pick a point here, I'm crossing once, it's going to be in. If I pick a ray that goes in the other direction, I'm going to cross 3 times, it's still in. So I'm saying it doesn't matter which direction.
Yep, I get it. Yep.
You get it, okay? And now we can complicate it again for us. We can have, so here is a non-simple one inside of a simple one. But the rule still works, so we can have multiple of these, and it gets more complicated. Okay?
What is an angle polygon?
Coming to that. That's what's called a winding polygon now. But let me just, before I go there, I'm going to just do ray crossing in 3D. So we see that it works out exactly the same way. And here, so I have a closed oriented surface. There are multiple surfaces.
Yeah.
Okay.
I can see this is going to work. Yeah.
Okay. But you see it's going to work out exactly the same way. The ray crossing count is going to be odd. Okay. And the examples come out exactly the same way. I have a simple, even convex polyhedron, and you see these blue points inside are in, the ones that are red are out. This is simple but not convex, and so on and so forth. Okay, and you get these multiple nested ones, and you have a way to determine what's in and what's out.
A comment from our live stream is make sure to handle cross-polygon vertices properly. In other words, I guess if the if the rays go through,
Yes. Okay. So there are 2 ways of handling that. One is that you The one way is that you derive a calculus for how to compensate for it properly, and you can kind of pull through that in 2D. 3D, it gets very complicated because you get edges and vertices both to deal with as boundary cases. What you can better do is that if you hit one of those, you're going to hit one of those with probability 0, you pick a different ray. You start over.
Okay. So, you mean probability what? If you hit?
If you pick the ray that so happens to go through a point.
Yes.
You can detect that. You start over, you pick a different ray, and you're going to hit one. You're not going to hit one. Same if you hit an edge.
Yeah, fair enough.
Okay. Now, angle polygon. This is the other way, common way to define a polygon. And I'm going to use nomenclature now that's going to generalize to 3D. So, but you're going to like it in the end. Okay. So, so this is just a different way of a way of defining angle. So I want to see for an edge, for a segment, for a face of the polygon, or an edge as we call it, or facet. Okay. This is the subtended angle. So here's a point. I want to figure out whether it's going to be inside, and I want to see what the edge, what's the angle is that's subtended by that edge.
Yep.
Okay. That is the angle as I traverse that. Okay. And it's oriented.
Yep.
Okay. And we can go different directions, right?
By the way, isn't there a geo analog of that computation?
Maybe.
I think it's the conversion between grid and grid coordinates and lat long coordinates or some such other thing.
Okay.
Anyway, okay, go on.
So we have now an angle measure. So I'm going to define that angle measure. So I have a like we did before, I have a closed contour, piecewise linear, let's say, and it's oriented. And then the angle measure is that I'm adding up with sign what the measures are. So I take each segment, in this case positive, or if I go this way, and I just add those up.
Okay.
That's my angle measure. Now that I know what the angle measure is of the boundary with respect to that point that I'm checking, now the only if I have a simple, so the boundary doesn't cross itself, the only possible values that measure can have is these -2 pi, 0, and 2 pi. And if it's not simple, meaning it crossing itself, then it's any integer multiple of 2 pi.
Okay.
Okay. So that's what can happen. Now I can use this. So I define a polygon. So a point is in it if that angle measure with respect to that point is not 0. See what I'm saying?
Yeah, okay. I get it. Yeah.
Now, I can also do, if I have multiple closed and oriented curves, I just add all of them up together, and I get something for multiple closed curves. Just as we did for ray crossing. I did a case for multiple closed curves.
All right, so go. I mean, I think I get this, but okay.
Okay, we get in there, Stephen. We're going to do this for Polyhedra next. So I just want to do this base case better. Okay, so it behaves like you think it is. You know, people learn like rules, like put your finger in the middle and sort of wind around. And so, how many times does a rubber? You know, how to count these angles. But you see, these points are in because I'm going to wind around once, so it's actually 2 pi. For any of these points.
I think, by the way, the person on the live stream is talking about if polygon is to test whether the polygon is inside, take 2 points in order and the polygon together with a random point and calculate if they make a clockwise or counterclockwise turn. Is that equivalent to this, or is that not equivalent to this? In other words, if you sit inside a polygon and you look at the polygon vertices in order,
I think that's going to come out to be equivalent because there are many ways to get this equivalent.
Yes.
I picked an explanation here. I did it the traditional way, and then I redid it so that it fits the 3D case.
Okay.
Okay. So that's why I've done it this way.
Okay.
Okay. And it behaves. This one is, one thing to note here. For the ray crossing case, these inner points would have been out. these blue points in that middle part here, they would be excluded if you use ray crossing. But they're included with
Yeah,
this
I get
rule.
it. I get it. I get it.
Okay.
Yep.
And likewise, you can get.
What are situations where all this stuff really matters? I mean, I understand one has to get
different communities have different conventions for what they really like as their polygon definition. And so for some people, it doesn't matter that much. But Adobe, for instance, support both what we call here winding or angle.
Yeah, I remember that. Right. Even in an early PostScript, that was the case.
Right. But they call it fill rule because they don't really compute with it. They only sort of fill. Do you know what I'm saying?
But they care about it. Do they care about it because they're trying to make a letter A with a hole in the middle of it?
They do care about it. Yeah.
For that reason? I mean,
yes.
For fonts?
Well, yes, that's one reason. That's probably why they had it early on, I suspect, actually.
Mm-hmm. How do we do fonts? I mean, when you take a font and we import it,
it becomes a filled curve. Our filled curve does exactly this, with a ray crossing case.
Okay, but our filled curve is what? It's one of these polygons?
Filled curve. No, filled curve is like a meta primitive. You can have lines and Bezier curves and B-spline curves as segments.
Yeah, I understand that, but how does it know what the inside is?
It ultimately discretizes and using it for polygons. Do you know what I'm saying? It discretizes so fine that you can't see it. It's at pixel resolution.
Okay, but I mean, if you have a letter A with a capital A with a hole in the middle, or a lowercase a with a hole in the middle, you're saying that it is, I mean, doesn't it have to assemble that from coordinate patches, basically?
Yeah, but it uses, if you import it and use it as a graphics primitive to render it at big size, otherwise the system does it, the operating system does it, and we don't do it.
No, I understand that, but I'm asking if in this model, what you're defining here, you could make an A that is a single polygon. Is that true?
That's true.
Okay.
And that is
what's done in typical. I have no idea. I mean, I don't know the details of how fonts and type 1 versus true type versus whatever else. I don't know the details of how those are, how those are represented. But is it?
They use B-spline curves. So the true type font uses B-spline curves. The Adobe used Bezier curves, I think.
Yeah, right. Okay, fair enough. All right. Okay, keep going. Yeah.
Okay. So, and here's how this comes out. Here's two closed contours, and applying this rule, they're all in.
Mm-hmm.
Okay. And you can see how all the different cases. So for simple polygons, everything agree. When you get to non-simple, multiple class contours, they disagree, the different definitions. So there are different ways of defining what the set is. Do you know what I'm saying? What's in it, what's filled.
Yep.
Now let's do the 3D case, and then we're done.
Okay.
There are many other kinds of polygons here that we're not going to talk about. Okay. Now, since I did the derivation with an angle segment to a unit circle, now you can see what the subtended angle, this is a solid angle, is from a sphere. So the point is at the center of the sphere, and how much this polygon subtend from that sphere.
Mm-hmm.
Can you see that? And they can also be oriented. So these are two different measures here.
Yep.
Okay. That means that we've defined what the angle measure is, right? With respect for a polygon with respect to a point.
Yes.
Okay. So now, so for a closed polygon, an oriented polygon surface, we just compute the total angle measure for each face. Do you know what I'm saying?
Yeah.
Okay. I mean, with sign.
Yeah, so they're signed angle. Yeah. So
they're signed solid angles.
Yep.
Okay. And if you have multiple surfaces, then you just total up each surface on its own, which itself then totals up each polygon.
Yep.
Okay. Now I can define a polygon. Polyhedron. So first of all, the only possible, if it's a simple polyhedron, the only possible measures it can take are these: -4 pi, 0, and 4 pi. Just as in the polygon case, the only possible values was -2 pi, 0, and 2 pi. And if it's non-simple, if it crosses itself, it can be any multiple of 4 pi. Make sense?
Yes.
Okay. So now we define that polyhedron, what a point is in it if the angle measure is non-zero. You know, and it's the same for when
I get it. This is beautiful. Right.
Okay.
It's very nice.
So now, so those are, those are kind of key, and now we can do a bunch of examples for that, and then we're done.
Okay. Roger, practicality. I am supposed to go to some other meeting right now. We clearly have a fair amount more to do for this computing.
We will set up another one, okay? We'll immediately ask.
How long do we have? We're going to need 2 hours at least, I think.
I think so too.
Can we just scope out? Let me get my screen back for a second. Let's just scope out what we have to look at. Okay, convex polygon, simple polygon Q. That's reasonable enough. Okay. Polygon decomposition.
So many algorithms. What they need is that you have an algorithm that can only work for triangles. You have an algorithm that can only work for convex polygons. You have an algorithm that can only work for simple polygons. So now if you have something more complicated, you got to break it down into these things.
By the way, I think this should say polygon decompose, because I think this is returning the actual decomposition. Whereas usually when we have something called decomposition, it gives an object that represents, you get what I'm saying?
Well, you could argue both ways. You know, if you say LU decomposition, it gives the actual decomposition. Jordan decomposition gives the actual.
Yeah, I was thinking of those examples, but they give sort of a package that is assemblable into the decomposition, whereas this is actually decomposing the polygon into the convex pieces.
Right, but you can assemble it by union.
Well, I understand that, but, well, whatever.
I mean, I'm not opposed to whatever you know.
I think polygon decompose might be better for this, but I'm not sure. Okay.
So now you're going to see that the polyhedron case follows exactly, pretty much exactly.
Okay, so are you saying that uniform polyhedron takes all the strings that are in polyhedron data?
No, only the ones that are uniform polyhedra. So there are things that are not there, and all the things that are there are the same.
Okay.
Polyhedron data doesn't include all the uniform polyhedra, unfortunately.
How many more are there?
Charles, what's the count?
Well, polyhedron data, I mean, it's hard to actually build them, is what we are building now. So polyhedron data just have 22 of them, excluding the infinite family, prism and antiprism. So there are 75. We are building all the full 75.
Okay, great. Are we getting exact coordinates for them and all kinds of crazy stuff like that?
Yes. Painful, but yes.
This is this crazy bounding box issue again for 3D graphics. We keep on talking about this.
So U2 is implementing another thing to give you where you can give the actual sphere that you want as the bounding.
Okay.
Okay. And that will solve the molecule case, because if he just had points, right? He can use bounding region to get that sphere, and now he can call graphics appropriately, and it will be what you want.
Excellent. So using the min ball business and things like that?
Exactly.
That's beautiful. Is that efficient?
Yes, very.
Okay. Okay, all kinds of angle measures. Terrific. We looked at a couple of these. All right. Okay, so just to scope this out. Okay, graphs and networks, we did the review of that, right?
We did, yes.
Okay, so UnityLink is another probably, is that a 1 to 2 hour design review at least?
Yes, but they will not come this week.
Okay. Okay. Okay, well, all right, so another 2 hours probably on all of the stuff.
Yes.
Okay, wonderful. All right, let's wrap it up here. Thanks to folks on the live stream. And by the way, for those on the live stream, our marathon session continues with natural language processing coming up next. All right, I will commit these changes in a few minutes.
Okay.
Here. Okay, terrific. All right, talk to you all soon.